Okay, and we're live. Okay, so chemical reactions. Let me bring up my classroom here. Oh, and of course, my whiteboard. There we go. Chemical reactions. And you'll also probably want to have your periodic table of choice ready to hand as well. The one in your book will be adequate if that's what works for you. But most of you have like a better one from lecture. Okay, chemical quantities and reactions. So let's start with the basics. We're going to be looking at Avogadro's numbers, what it means, look at the molar masses. 1 mole of something is an Avogadro's number of something. Look at balanced equations and look at various types of equations, including combination, decomposition, replacement, both single and double, and then combustion as well. Look at reduction and oxidation reactions, and touch briefly on exothermic and endothermic style reactions. Okay, so at the top, so with a mole is just a term designating a certain number of something, just like a dozen of something is 12 of something. A mole of something is 6.02 times 10 to the 23rd of something. But a dozen of something is 12 of something, a case of something is 24 of something, and a gross of something is 144 of something. It's just words we've picked to indicate a number. Okay. And like I said, 6.0, actually 6.023, 6.02 times 10 to the 23rd is equal to a mole of any given item. It can be a mole of atoms, a mole of cans of pop, whatever. Okay. Named after someone who was born in 1776. I don't think they really knew what it meant back then. I think to them that was just an unimaginably huge number, and and they just called it Avogadro's number. Okay, and now we know that Avogadro's number is really not that big at all, actually. Okay, so like I mentioned, a mole of something is Avogadro's number of an element, 6.02 times 10 to the 23rd. A mole of carbon is 6.02 times 10 to the 23rd atoms of carbon. And a mole of sodium, of course, is 6.02 times 10 to the 23rd atoms of sodium. Okay, so far so good, hopefully. Now, adding to this idea a little bit more, a mole of aluminum and a mole of sulfur is that number of atoms of both aluminum and sulfur. Now, in H2O, we have 6.02 times 10 to the 23rd moles of H2O. Okay? How many moles of hydrogen do we have in a mole of water? Okay? Nope. Exactly. See, H2O, we have 1 mole of H2O, but since we have 2 hydrogens, we actually have 2 moles of hydrogen in a mole of water. Okay, that's an important thing to kind of keep in mind. Okay, and a mole of vitamin C has the chemical compound C6H8O6. There are 6.02 times 10 to the 23rd molecules of vitamin C. All of this over here. Okay, moles of vitamin C and 1 mole of vitamin C. So let's ask, how many moles of oxygen do I have in 1 mole of vitamin C? No, we have 1 mole. They said there's 1 mole of the whole molecule. Okay, that's there would be six. Exactly right. So in 1 mole of vitamin C, we have 6 moles of carbon, 8 moles of hydrogen, and 6 moles of oxygen. Okay. I'm going to come back to this concept. 1 mole of what? Of the whole molecule. Right. hmm And I'm going to come back to that. I just want to kind of plant this seed. And of course, sodium chloride, 1 mole, there's only 1 mole of sodium and 1 mole of chloride in that. Okay. So other things we can, so there are a lot of things we can do. It's a very useful idea, Avogadro's number. And it just happens that that number of atoms or molecules tends to be kind of a nice number that we can work with at our level of bigness, if that makes any sense. 1 molecule of carbon is so tiny, it's kind of hard to work with. So we usually in labs work with molar quantities to come with. So 1 mole, 6.02 times 10 to the 23rd particles. Those are equivalent terms. So we're going to calculate atoms or molecules. Okay. So the first thing we'll do is do a conversion from the number of moles to the number of molecules. And the question here, Avogadro's number is how many, let's get rid of all of this. How many CO2 molecules, okay, are there in 1/2 of a mole of CO2? Okay, so this should look kind of familiar. We'll set this up as a conversion. Okay, so we have 0.5 moles that were given. Okay, and 1 mole is of course equal to 6.02 times 10 to the 23rd particles. Okay. Now, just like we did before, let's make sure that we set this up right. Our moles cancel, and that leaves us with a number of particles. You take out your calculator, 6.02 exponent to the 23rd. Okay, you can see that. It's going to be, is it coming out right ways or backwards? But yeah, 6.02 times 10 to the 23rd times 0.5 gives us 3.01 times 10 to the 23rd. 10 to the 23rd what? Molecules of CO2. Okay. Okay, there it is, Avogadro's number. We set it up just like I set it up, 0.5 moles of CO2, 6.02 times 10 to the 23rd molecules of CO2 per mole. The moles of CO2 canceled out, leaving us with 3.01 times 10 to the 23rd molecules of CO2 in 1/2 of a mole of CO2. Okay, let's do another example. Another example is always good, right? So what is the number of atoms in 2 moles of aluminum? Cool. Very similar. Okay, so we have 2 moles of aluminum. We convert it that 1 mole of aluminum is the same as Avogadro's number. Okay. Make sure moles of aluminum, leaving us with that many particles. So once again, 2 times, well, let's go 6.02 exponent to the 23rd times 2 gives us 1.20. No, I only have 2 significant figures. So 1.2 times 10 to the 10 to the 24th. Okay. My rainbow. Right there, 1.2 times 10 to the 24th. Just like we were doing conversions earlier. So we're building on that concept, and now we're actually applying it. So 1 mole of aluminum is Avogadro's number of aluminum. Set it up. 2 moles of aluminum, 6.02 times 10 to the 23rd atoms of aluminum over 1 mole of aluminum. Cross out, leaving us with the atoms. And so the answer was C. And see, 1.2 times 10 to the 24th right there. Okay. So let's do another one, but we'll reverse it a little bit, but it's all the same concept. We're just going to rearrange things a little bit. What is the number of moles in 1.8 times 10 to the 24th moles of sulfur? Okay. Okay, so the number, atoms, sorry. Atoms of sulfur. How many moles is that? Okay, so let's set it up. We're given 1.8 times 10 to the 24th atoms. Set up our converter. So 1 mole is equivalent to right? Make sure that we cancel these out. We have 1.8 times 10 to the 24th atoms. Atoms cancel out, leaving us with the number of moles. So 1.8 exponent to the 24th. Let's see. Divided by 6.02 exponent to the 23rd. And that gives us 2.99, so we'll round it up to 2 significant figures, 3.0 times, not times anything, just 3.0 moles. Oh, right, 3.0 moles. So 1.8 times 10 to the 24th atoms is equal to 3.0 moles. Okay, and let's look at how we set this up. Just so. Okay, 1.8 times 10 to the 24th atoms. 1 mole is equivalent to 6.0 times 10 to the 3rd. Atoms cross out, leaving us with 3.0 moles of atoms. So the answer was B, right there. Okay, so far so good-ish, or we're kind of getting the hang of things? Okay, good. Asked after class, I'm also recording this as well. Okay, so moles of elements in a formula. Now we're going to return back to that idea why I asked how many hydrogen molecules there are in a mole of water. Now we're going to get to apply that. So we're going to look at aspirin, and I'll just ASA, acetylsalicylic acid, has the formula of C9H8 and O4. It doesn't tell you anything about its structure. It just tells you what the atoms are in that formula for that molecule. Okay, so there are 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen in 1 mole of aspirin. Okay, so let's use this. Like I said, 9 moles of carbon, 8 moles of hydrogen, 4 moles of oxygen, right there. Okay, so that gives us, so we have some built-in conversion factors for the number of moles as well as Avogadro's number in there. So if you're given a compound, I'm going to follow the same thing. We're going to write down what's needed, set up a plan for the conversion, and then run the calculation. Okay. Okay. Let's get rid of this. How many moles of oxygen are there in or how many atoms of oxygen are there in 0.15 moles of aspirin? Okay, no, I guess I did need that. C9H8O4, and we're given 0.150 moles of aspirin. Okay. So let's set this up. We're given there 0.150 moles of oxygen. Okay, and in every molecule of aspirin, we have 4 moles of oxygen, right? So the conversion looks like this. For every 1 mole of aspirin, we have 4 moles of oxygen. Excuse me, moles of acetylsalicylic acid. Okay. So let's cross these out. Our moles of aspirin, across from our moles of aspirin, for every mole of aspirin, we have 4 moles of oxygen. Okay, but they didn't ask for how many moles of oxygen they have. We have. They asked for how many atoms, so we need that second converter to get there. And for every 1 mole of oxygen, we have Avogadro's number of oxygen. Okay, now let's see. Moles of oxygen cross out, moles of oxygen cross out, and leaves us with the number of atoms. So we just perform a calculation. 0.150 times 4 times 6.02 exponent to the 23rd divided by nothing. Okay, divided by 1 and divided by 1. So our answer is the number of atoms of oxygen in a mole of aspirin is 3.61 times 10 to the 23rd atoms of oxygen. Okay. Right. So the secret to these, look at what you're given, look at what they're asking, and make sure that and then make a plan, come up with these converters to get from what they've given to end up with what they're asking. Okay, so molar mass. So hopefully you've gotten your hands on a periodic table near to hand that has the molar mass right on it. And this is where that's going to come into play for the following sets of calculations. Okay, so the molar mass of the element is this, for instance, for sodium, atomic number 11 has a molar mass of 22.99 grams. Okay, and all that means in 1 mole of sodium, a 1 mole of sodium has a mass of 22.99 grams. Okay, so that's like something that we can work with in a lab. That's like, 2/3 of an ounce or something. Okay. And for instance, if you look at carbon, atomic number 6 on your periodic table, it has a molar mass of 12.01 grams per mole. Lithium has a molar mass of 6.941 grams per mole. Okay? That's just express the amount of weight in grams that you have in a mole of those atoms. Silver, same thing. Carbon, sulfur, that bottom number. They're all to 4 significant figures. In this case, 4 significant figures to help us in our calculations. Okay, molar mass is the number of grams in a mole of that atom. Okay. So if you want to find the molar mass of a compound, we hopefully simply, multiply the molar mass of each of the elements by its subscript, or the number of atoms in that compound, and then add up the results. So let's look at an example. So I have lithium carbonate. Okay. Lithium carbonate, like so. Okay, so we want to know the molar mass of 1 mole of lithium carbonate. So lithium has a molar mass of 6.941. Okay, molar mass of carbon is 12.01, and these are just from the periodic table. And the molar mass of oxygen is 16.00. Okay? It'd be nice if now all we had to do is add these up, but there's an extra step. And the extra step is we look at lithium, and we see that for each lithium, each mole of lithium carbonate, there are 2 moles of lithium. There is 1 mole of carbon, and there are 3 moles of oxygen. Lithium, carbon, and oxygen, right? So these numbers, of course, correspond to these subscripts up here. Perform the math, and actually I think I'll just roll down rather than do it. So 13.88 grams of lithium, 12.01 grams of carbon, and 48 grams of oxygen. And then we just add all of those up, and the molar mass, drum roll here, of lithium carbonate, whoop, that was not very good, but get the gist. Add those up, and 73.89 grams of lithium carbonate in 1 mole. Okay. All right, so let's do another example. The molar mass of this right here, and 1 oxygen. Okay. Okay, so the first thing, what was the molar mass of carbon? Okay, molar mass of hydrogen is, look on your periodic table, 0.8. Okay, and molar mass of oxygen is from above 16.00. Yeah, no reason. Actually, I'm going to stay consistent because I just pulled that straight off a periodic table, but I'm going to keep 1.001. Okay. No, that's four. That is 4 significant figures. I'm sorry. They had it right. 4 significant figures across the board. Okay. So the number of carbon atoms we have in a mole of that is 2. The number of hydrogens is 6. The number of oxygens is 1. Do our arithmetic here. Let's see if I can. 24.02, and that's going to be, well, that's going to be 16, and that's going to be 6.048. Yeah, just round it up to 6.06. Okay. And then you add all of those up. So the approximate molar mass of that compound is 46.08. Units are grams. Never forget the units, what units you're working in. Okay. Whoa. Get out of here. Whoa. Okay. Microsoft. Okay. All right. So and I think kind of the last little thing we'll look at today and then circle back, start tomorrow. Molar quantities. This is they've measured out gram equivalencies of sulfur, iron, salt, sodium chloride table salt. Was that potassium chromate and some organic compound. I don't know which one that is. Right there. Okay. Molar mass of all of those. So each one of these contains a mole of what they are. Okay. So obviously, if we can move in that direction, we can also use this concept to move in the opposite direction. So if you want to find out what the molar quantity is of something, and you're given the molar mass, you can reverse engineer that and come up with the answer. Okay, so we have a compound, methane, CH4, simplest organic compound. The molar mass of methane is, and they already did the math, but just in case, so we have 12.01 times 1, and hydrogen we have 1.008 times 4. We do that math, and the molar mass of methane is 16.05. That's where that came from. Okay. So, last question we'll look at today. We're given that we have 737 grams of sodium chloride. How many moles of salt do we have in 737 grams? Well, the first thing you're going to need to do is calculate the molar mass of sodium chloride. Go to your periodic table and you find out that sodium has a molar mass of 22.99 and chloride has a molar mass of 35.45. Okay, add those together and you get 58.44 grams per mole of sodium chloride. Okay, now we have everything we need to complete this problem. We're given that we have 737 grams of sodium chloride. For each one mole of sodium chloride, there is 58.44 grams of sodium chloride. Okay, let's make sure that our units cancel out. Grams of sodium chloride leaves us with a number of moles. And then I'm just going to let the slide deck do the math for me. Basically, 737 divided by 58.44 gives us 12.6 moles of sodium chloride in 737 grams of sodium chloride. And let's see. I'm going to stop there, and then we'll do an example along these lines to start class tomorrow to kind of lead us in a good spot. Okay, actually, let me stop the recording.